Codemotion.
I can start? Sweet. All right. Thanks for coming to my session. Thanks for having me here. And I apologize for not knowing any Italian other than my name is James and can I have this dish or that dish? So today I'm going to present to you on WebGL and Three.js. And I should probably put on my glasses. Whoa. One sec. This is so I can look smart. All right, so my name is James Williams. My email is up there. I work for a company called Reardon Commerce, but that doesn't really matter to this talk because that's in the travel industry. It has nothing to do with gaming or graphics or anything. So a little bit about me. I've written a book called Learning HTML5 Game Programming. It came out in October, and it's available in paperback and in Kindle form, and it's on the Google Play Bookstore. I have to do this plug, and this will be the only one for this talk. You can find me on Google+, Twitter, or I blog occasionally at jameswilliams.be. I'm not from Belgium, but my name's really common in the United States, so it was either be or nothing at all. All right, so our agenda for the day, we have some latecomers. Go ahead, get seated. We're going to talk about basically WebGL and Three.js, how they interplay together, talk about the different components of 3D modeling, so your shaders, your materials, your meshes, and how those all interact together, how to use different shaders to make very spiffy animations and effects. And we're going to close with some debugging tips. So WebGL is a sort of variant of OpenGL, if you are aware of that. It's based on OpenGL ES embedded systems. And OpenGL ES is the OpenGL that you would have on, say, your Nintendo DS, your PlayStation, Xbox, that sort of thing. It's a very low-level language API, and it's like 20-something years old. It's not very fun to work with. So just to jump into some code right now, this is how you would create a context, create kind of a surface to draw WebGL. But we're not going to stick with WebGL because, like I said, it's very nasty, and you have to think about a lot of things that are not fun for somebody who's just jumping in this and wants to play around. So we're going to switch to Three.js, which is an abstraction layer over top of WebGL, and it's a scenegraph library. So instead of having to worry about all the different points that comprise an object and where those points, where that collection, where that array or something is going to live, you can say, I want to draw a mesh. And it's going to look like this, and these are the vertices, and these are the different surfaces, and it makes it a whole lot more manageable. And you're able to render to the canvas, which is just a regular 2D surface, WebGL, which is 3D, and then also SVG, but nobody really uses SVG. And it supports a bunch of different 3D formats, like Blender format, 3D Studio Max. And just to let you guys know, you can interrupt me pretty much anytime with questions, so don't feel scared to ask a question. And you can find it up there on GitHub. So here is a basic Three.js scene in JavaScript. So we start off with specifying the test. Okay. We start off with specifying the height and the width, and the next three lines there is a renderer, and that's basically our way of drawing stuff on the scene with WebGL. It's kind of the master class that does all the work. So we set the size of our renderer, and then Okay, and then we use our camera and our scene and add our objects, and then lastly we add the renderer to our actual HTML page. So I talked a little bit about the camera before, but let's go into detail with that. And I apologize for having to like almost swallow the mic, but it cuts in and out. So like that. All right, so there are a couple of different variables that define what a camera can do. The first is the eye point, and the eye point is the space, the position in the physical world where the camera is. So if I'm a camera, this is my eye point right now. Next, you have to consider the field of vision, and the field of vision is the number of degrees on each side that the camera can see. And then the next is the near and far viewing planes, and those are a way to reduce the amount of stuff that we have to render, because you shouldn't have to render the stuff that's behind the camera that you're never going to see. So after that is the look at point, or the target. And with the target, there's also an up vector, which determines the sort of how the camera is oriented in space. So if you have, your up vector of being on the y-axis up, your camera's going to be upright, versus if it's -1, your view is going to be upside down. And there are a couple of different camera types that I'm not going to go into that Three.js has, like Quake cameras and Fly cameras. Pretty much any camera that you can do in a first-person shooter, it's already in there, or you can make it yourself. Okay, on to meshes. So there is an important variation that you have to do with meshes. With geometries and meshes, is a geometry is how an object is drawn, and the mesh is how the object is drawn along with the material data that corresponds to that object. So we might have a plane geometry, but we have a mesh that is a plane that comprises of the geometry and then whatever materials and stuff like that. So there are a couple built-in geometries. There are planes, like I said before, spheres, cubes, toruses, cylinders, all weird type stuff like that. And these next two code brackets that I'm going to show you is how you would draw an individual vertex or an individual face or surface of an object. And if you've had 3D graphics class, it's pretty much the same thing, it's just slightly different syntax. And here is how we would draw an actual object. So we start off with our geometry, and then to our vertex array, we add the 3 vertices, and that's assuming that vertex 1, vertex 2, and vertex 3 are defined somewhere else. And then we add our face, because we have the vertices, but we need to know how to draw the actual surface. And then we end with, okay, okay, all right, so we end with creating the mesh by attaching the geometry and a material, which we'll get to in a second. Oh, and here is an example how you could do it with one of the predefined geometries. The plane geometry, this is 200 pixels by 200 pixels square, and adding it to the scene right there. All right, so we're gonna go into our first demo, and dang it. It's, all right, well, what you were supposed to see, like over here, was a square. But let's look at the code right here. Okay, so we can see for our triangle, we have the vertices that we added, and we created the face, and we created a mesh. And then way down here, we added. Okay. All right, so lighting. And I just have this one slide about lighting. It's really important, but it's really boring. So I'm not going to spend that much time on it. But lighting affects how we view things in the world. There are a couple of different types of lighting, especially when it comes to gaming. The first one is ambient lighting, and that's kind of the base lighting that's in a scene. It doesn't cast a shadow. It's kind of there. It's kind of like mood lighting a little bit. The next type is a point light, which is a light at a specific point. It can cast a shadow and other things like that, have a specific intensity. The same with directional lights. And directional lights, I believe they don't cast shadow, but whatever, it doesn't matter. And then spotlights. Like I said, really boring. Any questions so far? Okay, cool. All right, so we're gonna go through shading a little bit. and okay. There are a couple of different types of shading. The first one up there is flat shading, and that's just kind of a matte, sort of not interesting base color. The next one is Lambertian shading, which is kind of like a diffuse shading. It's where all the different light rays that gets shined on an object gets scattered off in different directions. So like the concrete wall would be kind of a kind of example of diffuse shading. The next one is garage shading, which basically states that to calculate how to shade something, you're going to go on every single vertex and figure out the average between the vertices on a specific face. And the last one is Phong shading, where you also do every vertex, but you also do every pixel. So kind of in order of the easiest to do to the least to do, there it is up there. Garage shading will give you things that are somewhat kind of more realistic, but Phong shading, if you have the means to do it, it's kind of the best one to do. And there are also materials, and I just explained them for shaders. It's the same for materials. So there you got it. And we have another demo. And here. All right. So this is a triangle where I use vertex colors. So this is the red, green, and the blue. And if we go over here, up here, all right. So up here, where it's flashing, that's where I set my color for my red and my green and my blue. And then down here, where it says vertex colors, that's where I assigned it. And you can't see a square, but there's a square that's a matte blue color of 88F. All right, so we can also do texturing, and texturing, you can either pass in your own image data or load it from an image tag. And all of the preset geometries, like your squares, not squares, your planes and cubes and spheres and all that stuff, they know how to do their texturing. So you can just kind of say, texture this thing, and it knows how to do it. For your other objects, you kind of have to do that yourself. And that's when texture coordinates come into play. And assuming that this is a square texture, we would map it onto an object by passing in the coordinates of some that range somewhere from 0 to 1 on both the y and the x to each face. So like I was saying before, when you have a preset object like a sphere in this example down here, it already knows how to texture itself.
Go back.
And I'm going to do different simple. All right, so here is the sphere represented by that same code. I had a texture of the Earth and mapped that to that sphere and had it rotate and all that stuff. And I haven't talked that much about rotation as much, but every single object in Three.js has a rotation object on it. And if you want to set the y rotation, you just do object.rotation.y equals whatever. And same for the x and same for the z. Okay, so you can also load models, as I was saying before. You have to convert it to the sort of JSON format that Three.js likes, but there's nothing keeping you from using your favorite Blender or Maya or 3D Studio Max stuff. And I'm going to skip over that demo. All right, so here's to the kind of hard stuff. So GLSL stands for, I forget what it stands for right now, but it's a shader language that describes how to draw stuff when you want to do stuff that's more complex than just a flat color. And it uses a C-like syntax, which kind of sucks, but you know, that I didn't make it, so. And it allows you to target the graphics pipeline. And there are two parts of a shader program, is what they usually call it. Fragment shader and a vertex shader. Now the fragment shader is just a spiffy name for pixel shader, so that you can have a specific unit of code be applied to every single pixel in a mesh. And the vertex shader, as its name states, is just for the vertices. You can also communicate between the two of them, and you can generate them at runtime. So like I was saying before, a vertex shader is run on every vertex in a mesh, and it can alter the color, position, texture coordinates, anything that you can apply to your vertex, you can use in a vertex shader. And here is an example of a vertex shader. And like I said, it's nasty C code. This is kind of the most basic one that you would ever have, and it's saying for every vertex, do some 3D math and just put it on the screen. But this is all being done for you behind the scenes with Three.js with every single object that you draw. And pixel shaders can do more sort of subtle things like bump mapping and shadows, environmental mapping, things like that. And here is a pixel shader that says, I want to make every single pixel in this object green. Yeah, because this is the red, the green, the blue, and then the last one is the alpha for the opacity. All right. And here's how you use both of them. If you don't like jQuery, you can do your document.element get element by stuff. But this fit on the slide nicer, so that's why I used it. And we have our vertex shader that we use in our material, our fragment shader, and then actually this line shouldn't be there. And then down here we assign it to our triangle. There are different variables that you can use. There are different variables that you can use in your shader programs. A uniform is a one that you set, and it's kind of like a constant or a static value. It never gets changed once you set it. Varying is like a traditional variable. It can change, and then your attributes are, I believe those are for just the fragment shaders. And then you have different types like Boolean and integer and floats and doubles and all that types of stuff. And you can also construct new types. So if I wanted to make a material that's, 3 different colors for the ambient, diffuse, and specular color and a shininess, that's how you could do it. And that one's boring. Oh, this one's cool. All right, so for this one, I created a shader, a fragment shader, and using the time element, it creates a custom color. It kind of cycles through a bunch of different colors. And this is just informational to show you what's going on behind the scenes when you do texturing. So for that globe about 10 slides back that I did, this is all going on in the background. So this is stuff that if I were using WebGL by itself, I would have to do this myself, which is not fun. And fragment shader for that. Okay, all right, animation. And I'm not going to talk about animation that much. I just want to show you a cool thing that I found and wired up in WebGL. So that's why this slide is here, because I want to show you a cool demo. All right, so you can animate objects, very intricate objects with bones and joints and all that stuff in WebGL and Three.js. And there are a couple of different types of animation, and yeah, let me just do the demo, because the demo's cooler. This is the one. All right. Where is it? Where's my zombie? There it is. Ah, dang it. Well, my zombie is like here. All right, let me do this. Okay, and refresh. All right, well, you kind of saw a zombie, but the screen resolution here is kind of weird for my computer. So, apologize for that. I don't know, I'm sorry. If you come up later, I can show you. Okay, 15 minutes. All right, let me wrap this up a little bit so I can have time for questions. All right, so my last section is on debugging WebGL, which is, definitely something that you should do because you're using your graphics processor on your machine, and if you don't do it the right way and you have a Mac, your lap will get very, very hot. And I don't know about you, but I kind of don't want to make myself sterile. So, all right. So the first one that I'm going to talk about is stats.js, which is a little widget that you can embed as a sort of heads-up display to tell you how many frames per second are rendering, the milliseconds that it takes to render a frame, and how many megabytes are being used for each frame. And I forget what megabytes is in Italian, and I hope that y'all know what that is, right? Yeah. Because I know in French it's like mega octets or something like that. But anyway, so it's available at the GitHub, and the code to embed it into a scene is really, really lightweight. You just instantiate it, drop it into a div, and then whenever you run your render function, you just do update, and it keeps track of everything. So the next one is the WebGL Inspector. And this one is kind of very similar to the Chrome developer tools or Safari developer tools, Firefox, where it gives you kind of a console where you can see a lot of different stuff. You can see the different textures that you're using, the different shader programs that you're using. You can step through your rendering step by step. So if you create a Three.js scene, you can go and see the WebGL that it's producing to make your rendering. So this is a really cool one that I suggest you guys check out. And before we get to questions, there's this other cool thing called Shader Toy, where you can go through and create different shaders. And this is, like I told you, this is nasty C code, but it has a bunch of presets in here that you can check out. And delete that one. And for some reason, it's locked up my browser. Yay! Okay, there it is. And I seem to pick the only one that doesn't render anything. So I am done, so I'm open for questions. Anybody? Yep.
What about performance?
The question was, what about performance? What specifically are you talking about performance?
We can use it on mobile devices.
Okay. Okay, the question was, what about performance and what specific domains can you use it? Right now, WebGL is not very well supported on mobile devices. I think Android might have just got it, but I can't be sure. You can go to caniuse.com and type in WebGL and see. Performance, it's not supported on IE, any IEs. It might be in IE 11, but Chrome definitely very well supported. Safari is well supported. Opera just got it a couple of revisions ago. So it's definitely something cutting edge, and if you have to have IE, there are little different tweaks that you can do. So there's like this one project that uses Java. So and this part is going to sound like totally nasty and blasphemous, but it uses a Java applet to render your WebGL code if you're running in IE, because IE does not support WebGL. Or you can do things like using the Canvas renderer, which is not as fun because it's not hardware accelerated. So those are the kind of things that you have to think about. Cool. Any other questions? Come on. Can you speak up? Oh. Okay. So the question was, is the shader code compiled? Is that? Okay. The shader code is not compiled until it gets passed to the actual WebGL program. So you can create strings of shader code on the fly, like the shader toy thing tried to do. So yeah, so you're not limited. You don't have to pre-compile everything, and nothing really is compiled until runtime. Yep.
Does it allow some kind of interaction, like read on the objects that generate something like this?
So are you talking about like physics interaction or just clicking?
Like events when you click on an object. Right?
Okay. Okay, so the question was, does WebGL or Three.js allow interactions such as clicking objects or interacting with objects? It does and it doesn't. So there's nothing sort of in the core of WebGL or Three.js that says, I'm going to click this object and give me an event. But you can do the things that you would have to do that you would do in regular 2D canvas. So you can fire off array and find, where that intersects, and then if your object is in that sort of selection area, that sort of thing. So you can do it, but there's nothing sort of built in, from the core to do it. So, anybody else? Yep.
Are there physics engines or collision detection engines, something like that, high-level frameworks to do gaming with that?
Okay. The question was, are there 3D physics engines that allow you to do game-like interactions? Yes, there are. There is one called Bullet.js, and there is another one called Jiglib, Jiglib. Both of those allow you to do physics-based interaction. And then there are a bunch of other people that wrote their own, like Box2D JS and stuff like that. So.
Are they product already? Are there projects around that use these frameworks, or they are still in beta or development?
Okay. The question was, are they production ready or are they in beta? Bullet.js has been ported from the C. I think it was in C first. So that one is very production ready. I've messed around with Jiglib a little bit. So, I mean, I think that all of them are pretty good, but the whole WebGL space is kind of beta already. So you kind of, just got to dive in and try and be awesome with the tools that you have. So, yep, back there. Huh? Could you repeat that?
The image of UV map. If I import a model from one modeler program,
Uh-huh.
what about the image of UV map?
Okay, UV mapping?
Yeah,
Okay, yeah, you can do that if you're texturing. I don't think that there are any. I'm not sure that comes over when you convert an object from like 3D Studio Max or whatever. I would have to check on that, but I think that there are some tweaks that you have to do. Like it pulls over the colors, but I'm not sure that it totally pulls over the textures without having to fuss with it and like flip normals and stuff like that. Okay, cool. Anything else? Yep.
Are there any animator software for WebGL? This kind of
Okay. The question was, are there any, okay, 5 minutes. Are there any animation programs for WebGL? Well, you can use, it does have exporters for 3D Studio Max and for Blender and then for Wavefront OBJ format, but those convert it into a sort of JSON format where it's, you know, more suitable for Three.js. But all of those have been around way before Three.js and WebGL, so they aren't specifically targeted to it. So, anyone else? Alrighty. If there are no questions, thanks for coming. Thanks for having me.
Codemotion.